Hello everyone and welcome back to my channel Gyan Sampada. In some of our previous classes we have discussed about basic principles of quantum mechanics and also its simple applications. And today I am going to discuss about another important concept of quantum mechanics which is generally confused under the name of completeness condition. And our today's topic is about the closure relation in quantum mechanics. Many a times it happens so that we think closure and completeness condition are one and the same. But we need to know what is the thin difference between the two, or what is the link between the two. And our today's focus will be on deriving this closure relation only. So as such, if we look at this heading, it is made up of two things. One is closure and another one is relation. So if we consider the first word, that is closure, means something which is closed. And in mathematics or in group theory, we just consider law called as closure law. That is, if we are considering different vectors and we do certain operations which gives another vector, and that vector again belongs to the same space, then we say that closure law is satisfied. So whether it is going to remain same in quantum mechanics is the question. So here we are going to make use of some basis vectors, the wave functions, etc. to understand about closure relation. So as such, closure relation is a mathematical statement that a basis exists and is complete, which means that there is neither missing terms nor extraneous or irrelevant elements in the construction of the basis. So this is what actually the closure relation in quantum mechanics speaks. So basis is the main thing here with respect to which we are going to explain about closure relation. So as such, the basis of a vector space is consisting of a set of maximum possible number of linearly independent vectors which are belonging to that space. So a set of vectors like phi 1, phi 2, phi 3, so on up to phi n can form a basis in a vector space, where these phi 1, phi 2, phi 3, so on are called as the basis vectors or base vectors. So this is what is basis. And now coming back to the closure relation, in order to derive the closure relation, we need to know some of the details. So first let us consider the discrete orthonormal basis in F. F is nothing but the field or the space where we are going to work out. So as such, if we want to define it, for that let us consider a countable set of functions of F which is labeled by discrete index I. So I can be 1, 2, 3, so on up to n or more than n. So we can say the functions like u1 of r belongs to F, u2 of r belongs to F, so on, ui of r also belongs to F, and furthermore functions are also going to belong to the field F. Then the set ui of r is said to be orthonormal if the inner product of ui with uj, which is shown in the integral form as integration of ui star into uj star into d cube r or d tau, is equals to delta ij. Delta ij is nothing but the Kronecker delta function, where this will be equal to 1 if I is equals to j, and it will vanish if I is not equal to j, which we are calling as equation number 1. So this inner product we have just represented in integral form. So left hand side term in the inner product, that is ui, will be shown with the complex conjugate, and the right hand side uj will be as it is. So d cube r means it is a volume element which can be shown as d tau also. So it constitutes a basis, that is ui of r, if every function xi of r which belongs to the field F can be expanded in one and only one way in terms of ui of r. So here the basis, that is the set ui of r, constitutes a basis, means it is sometimes said to be a complete set of functions. And in that case, we can define xi of r as summation over I ci into ui of r, which is equation number 2. So these equations we have already studied, where ci is the coefficient which is called as probability amplitude also, which you can get it in the playlist section named Quantum Mechanics Basic Principles. And now let us study about the components of a wave function in basis ui of r, that is the set. So in order to get the components, let us consider equation number 2 and multiply equation number 2 by uj star of r, and let's integrate over all the space. So equation number 2 is xi of r is equals to summation ci ui of r. To this, on the left hand side we will multiply by uj star of r, means we are getting the inner product of uj with xi, because we know that LHS part of the inner product always means that it is the complex conjugate. So here in place of xi we can substitute summation over I ci into ui. So here summation ci can be taken outside, and finally we are having the inner product of uj with ui, and if we use equation number 1, this inner product will be equal to the Kronecker delta function, which can be either 0 or 1. So here we will consider I is equals to j, for which inner product reduces to 1. So we are having summation over I ci, which can be considered as a constant or coefficient Cj. So this is one approach where you can multiply equation 2 by uj star of r, or else we can just consider inner product of uj with xi of r. Both will get you the same result. So Cj is inner product of uj with xi. So Ci in the similar manner can be written as inner product of ui with xi, which will be equal to, in integral form, it is integration of ui star of r into xi of r d cube r, which we will call as equation number 3. The component of Ci of xi of r on ui of r is therefore equal to the scalar product of xi r by ui of r. This is what it means. So once the basis set ui of r has been chosen, it is equivalent to specify xi of r or the set of its components ci with respect to the basis functions. So once we will consider a set of functions which is basis, where it has a collection of all the terms denoted as ui of r set, and any wave function, let us say xi of r, can be expressed with respect to the basis functions which are again contained in the same set. So the set of numbers ci is said to represent xi of r in the basis ui of r. And I hope now you can relate the closure law here. So we have already seen equation number 1, which is called as orthonormalization relation, expresses the fact that the functions of the set ui of r are normalized to 1, and also it is orthogonal with respect to each other. So orthonormalization means orthogonality with respect to each other, and the set is normalized to 1. So in detail we have discussed about normalization or orthonormalization in our previous classes. If you have any difficulty, you can just go through it and continue with this today's class. And the relation which expresses the fact that this set constitutes a basis is called as closure relation. We know that any function has to be normalized, and any function can be expressed in terms of a number of wave functions which are constituents of the space which itself explains about the principle of superposition, and without violating any of the basic properties which we have already discussed, gives us the detail about the closure relation. So we can say that instead of certain scalars, we are having here proper wave functions or the basis vectors, which can be expressed in terms of different types of basis vectors. And finally, every element is going to belong to the basis set itself. Means we can observe the closed nature, and that's why the relation which explains all these things is called as closure relation. So this is about introduction or the foundation for studying closure relation. And now let us derive closure relation. So for that we need to consider the basis set ui of r. So if you consider it, then there exists an expansion such as equation number 2, which is nothing but xi of r is equals to summation ci ui of r for every xi of r belonging to f. So from principle of superposition we can write xi of r in terms of its constituents like ui of r or uj of r, etc. But whatever constituents or wave vector we consider, that will belong to finally the vector space f itself. Now substituting equation number 3 in equation number 2, that is we need to substitute ci value in xi of r. So by doing that we get the various components of ci, and the integration variable must be changed as we have already considered r in equation number 2. So now the domain has to change. So we can define xi of r is equals to summation ci ui of r, where from equation number 3 we have ci is equals to inner product of ui into xi and ui of r as it is. Now again substituting the value of inner product of ui and xi, instead of r we will denote as r dash to understand the difference between the previous notation and the newer one. Then ui of r will remain as it is. Let us call it as equation number 4. Now in order to solve it, let us interchange summation and integration. So by this we can write it as integration of d cube r dash into xi r dash into summation I ui of r into ui star of r dash. And we can consider this bracketed term, that is summation ui into ui star, as a function f of r comma r dash. So remember this r and r dash, everything is a vector, that is functions of both r as well as vector r dash, such that for every function xi of r we will be having xi of r is equals to integration of d cube r dash into xi of r dash into f of r comma r dash, and let this be equation number 5. And this equation number 5 is a characteristic of a function delta of r minus r dash, and from this, that is whatever we have discussed above, it can be deduced that summation of ui of r into ui star of r dash is equals to delta of r minus r dash, and this relation, that is equation number 6 itself, is called as closure relation. And if you just want to know about the closure relation for continuous spectrum, then we can just write, instead of summation, integration is added. First term we are writing as the conjugate, that is xi star of x dash k into xi of x comma k into dk is equals to delta of x minus x prime. So just we have changed the notations, instead of u we have taken as xi, and ui of r we have written as xi of x comma k. Here we have considered one dimension, that is only along x direction. So we can say that this is the integral form of closure relation. And now let us verify it, that is reciprocally or by converse. What does it say? Whether we are going to get back the same thing or no is the question. So if an orthonormal set ui of r satisfies equation number 6, that is the closure relation, then it constitutes a basis. This is what it is saying. If anything constitutes a basis, then it has to be an orthonormal set. Now we are just doing it in reverse order, that is by reciprocal. If orthonormal set itself is taken, and then equation 6, that is the closure relation, has to be checked, and if it satisfies, then we can say that set ui of r acts as a basis. And any function xi of r can be written as integration of d cube r dash into xi of r dash into delta r minus r dash. So again, all these r and r dash are the vectors. You can just put an arrowhead or else make it bold. So earlier we went from top to bottom, now we will go from bottom to up. That is what is a converse. Then we will substitute equation number 6 for delta of r minus r dash in equation number 7. And when we do so, we can observe that we are getting equation number 4. So again, interchanging summation with integration, we get equation number 4. Earlier was a previous step of equation number 5. Now by interchanging, we get equation number 4 itself. Therefore, this equation then expresses the fact that xi of r can be expanded in terms of ui of r and gives the coefficients of this expansion. So this is how we can explain about closure relation, what actually is a closure relation, what is the use of it, or what does it signify, then derivation of closure relation, and also the converse of it, that is reciprocally also we can prove the same thing just by going in reverse direction through all the steps. And many a times we just confuse between a closure and complete. That is, we say a basis has to be complete, which means that you can reach all the possible directions, or by which you can just decompose a vector into its components of the space. And in quantum mechanics, the state space is a separable complex Hilbert space, and by definition a Hilbert space is a complete inner product space. So whatever we have considered here is the inner product itself. And if you consider the outer product, then we observe the projection operators. So when you take the summation of the projector operator, we get finally a identity matrix. And the closure and completeness, we say the closure relation is a mathematical statement that the basis has to exist and is complete. And these states are said to be complete simply because they cover all the possibilities. And this is how we can link between the closure relation and the completeness condition. Completeness condition, already we have derived it, which you can get it in the channel. And this is about the closure relation, which is again an important as well as generally understandable relation in quantum mechanics, which is many a times used under the name of closure law in mathematics. So we can say that the expression of a closure relation can be given as a definition of the symbols used to specify the elements which are contained in the basis. And this is for today's class. See you in our next class. Till then, stay tuned, study well, and thank you for watching.